You're listening to Within Tolerance, a podcast for machinists by a machinist. I'm your host, Dylan Jackson of Proteum Machining, and this week I am joined by Zach Tong of Breaking Taps, the YouTube channel. Welcome, Zach. It's super cool to get to talk to you. I've listened or watched so many, hours or whatever of your YouTube channel, so it's really cool to get to talk to you in person and kind of nerd out on all the stuff you get to nerd out on.
Hey, yeah, thanks for having me. Appreciate being on the show. I've been binging through a lot of the episodes recently, so I'm still pretty far back in the catalog, but working my way up to modern day.
Awesome. Well, so for anybody who hasn't seen your channel, what's a brief overview of what Breaking Taps is and where can they find you online?
Yeah, so Breaking Taps is a channel that originally started for kind of machining content. That's how I originally started, and that's why it's called Breaking Taps, because I am a pretty terrible machinist, as I quickly discovered. It's kind of morphed over time to more material science topics and like optics and lasers and tensile testing of materials, stuff like that. And it's kind of skewed towards microfabrication in the more recent episodes. So it basically covers a whole bunch of stuff. I have a pretty short attention span when it comes to personal projects and stuff. So it kind of wanders around. Yeah, I guess that's a summary of it.
Well, very cool. Yeah, I think the first video, I want to say that the algorithm did good and recommended to me was your high-speed chatter one.
Yeah.
And for anybody, I'll link it in the show notes, but for anybody who hasn't seen it, you've got to go check it out because it is, really enlightening. I mean, you were doing it on a very lightweight machine, but even then, those core concepts apply across everything.
Yeah, that was a fun one. That was definitely the first video that kind of took off. Like before that, is your standard YouTube channel of just a guy playing around in his garage, and there's like 100 people that watch it. And the algorithm decided it liked that video. So I ran some tests on, I had an Avid CNC Benchtop Pro. It's like a pretty chunky benchtop router, but it's still just a benchtop gantry router. And I got a hold of a high-speed camera and basically just filmed it doing fun things. The chatter is not what I expected. Like you hear chatter, but seeing it actually like moving around the end mill and the spindle head moving was pretty impressive. And I did some other stuff with like audio acoustic analysis to try to see if you could analyze the chatter more than just listening to it with your ears, because our ears are really good at picking it up, but you can actually see that kind of in the spectrum of like an audio frequency analysis, which is pretty cool.
Yeah, definitely. I love that all of these concepts that were so feel-based for so long are finally getting quantified so that, us normal people can look at this data. I think there's been a lot of chatter analysis in labs and at, colleges, but nothing that has been widespread enough that I saw it. Talking to John from Corporate Patterns, he talks a lot about the kind of research they're doing. But again, it's not super available to the layman machinist. So it's really cool to see somebody like you taking care of that.
Yeah, it's neat to it's cool to see something visually that you can hear, right? Like I think everyone, you hear chatter for the first time and you know what's going on. It sounds pretty bad, but to actually like see it was really impressive. And everyone loves high speed footage too, so that helps.
Definitely. Well, let's get into your backstory. How did you get to here? Because I know I've done a little bit of research on your backstory, and it is pretty impressive. So let's talk about that.
I don't know about impressive, but it's definitely been all over the place. So I am technically a biologist. I have a degree in molecular and cellular biology. I worked in kind of like wet labs for a couple years and quickly decided that was a poor career choice. Just academia is really hard. Even if you are super dedicated and super smart, you just kind of have to get lucky, which wasn't something that I really won in my career. So I bailed on biology after a couple years in different labs and switched to software engineering. I'd always done software stuff kind of on the side and took it up as a career, worked in that for the last 10 or so years. Doing folks on this podcast probably don't care about the software side of things, but distributed search algorithms basically for a company. And then recently, about a year ago, I guess, I quit my job, mostly just because the timing was right. The company had changed a lot since when I joined it, and decided to become a full-time YouTuber, I guess. It's kind of weird to say it out loud. I don't really self-identify as like a YouTuber, but that's probably my accurate job description at the moment. mostly do YouTube stuff, but I'm working on some things on the side. So YouTube kind of helps pay the bills, and it's just fun too. I started the channel about 4 or so years ago, and so it's only recently sort of taken off.
Okay. And
So
then
that's kind of
how did you get into manufacturing? Like what made you buy your Avid and all of that?
yeah. So it started with I was working on a project 4 or 5 years ago, a little bit on the microfabrication side. So I've always been interested in like DIY transistors, that sort of thing. And I was working on a project in 3D printing stuff, and I needed more precision than I was getting out of my not very good printer back then. And so I don't know, I just started looking around, and around the same time, I think I had been just coincidentally watching a lot of This Old Tony on YouTube, who's kind of like the gateway drug to machining, I feel like.
For sure. Oh yeah.
Just it's so accessible, and everyone loves This Old Tony. So that started the rabbit hole, and then I started watching, Tom Lipton, Knox Tools, Edge Precision, the whole kind of set of machinists on YouTube. And I don't know, I just decided, hey, this looks cool. I'd done some woodworking, and it was kind of like woodworking, but harder, I guess. And found a little Rockwell milling machine locally, which was something because my area doesn't have a lot of industry. Like it's not an industrial base at all. So used machines are really hard to come by. But I found this little mill and started playing around in my garage. And that's when I started the YouTube channel. And it kind of just snowballed from there. I picked up a TAG locally as well. And I got real excited about it. I built like an enclosure and flood coolant. I only ended up using it for like one project, but it was really fun just getting into the CNC side of things. And then after that, I decided to just upgrade to the CNC router from Avid. Yeah, and then very recently, I just grabbed a Haas OM2A, one of those little office mills, which has been a bit of an adventure, but that is the most recent and more industrial, if you can call an office mill industrial equipment. So that's kind of been my progression so far.
What year is your OM?
I believe it's 2006.
Okay, I think you posted on the Discord that it's the 20K spindle or the something like
30K.
that. Oh, that's awesome.
Yeah,
especially for the stuff you're doing. I mean, all that micro stuff. I mean, I've got two 10K high torque spindles in my brother's, and this last week I was doing a bunch of stuff with like 20 thou mils, 15 thou mils. I'm like, this is painfully slow. Like I would love a 30K spindle or a 40K spindle for this kind of stuff.
Yeah, exactly. That's why I picked it up. I kind of over the years have I don't know if it's just because I'm drawn to small things or if it's because smaller stuff is easier to do in a garage setup. It's everything's smaller. So I saw it. It was a reasonably decent price. I'm like, oh, they'd be good to add for like micro machining stuff. My Avid has a 24K spindle. And so it's funny whenever I see machines that have like 12K, I'm like, that's so slow. How do you do anything with 12K? It's just my brain's in a different part of the ecosystem. But it's not super precise for micro machine stuff, and especially the Z-axis kind of struggles sometimes for lots of up and down moves. And so having a proper machine for micro machining seemed to make a lot of sense.
Yeah,
and I have a lot of plans to abuse it for projects. So once I get it up and running,
awesome. Yeah, it's micro machining is easier and more accessible from a like material standpoint. Like it's easier to get small pieces of material, but like, man, you start talking about like run out at micro scale and things like that, 1/10 of run out on a 1/2 inch end mill doesn't mean anything to me, but like 1/10 on a 10th out end mill is giant. So
yeah, I feel like I didn't know that at first. And so I'm like, this is easy. It's smaller stuff and smaller machines, but it just moves the problem somewhere else. And you just have a different set of things you have to worry about.
Yeah, but it seems like you have a lot of the tools necessary to kind of document and troubleshoot those as well. Like I think it'd be really cool to see what a tenth or two of run out looks like on a 10th end mill at high speed or something like that. Like you a lot of that, even for all the metrology equipment I have, is almost impossible to quantify. So it'd be really cool to see stuff like that.
Yeah, absolutely.
Well, we had a couple questions that I put up here. The first one from Moose Engineering, he just said a massive thank you because it's so cool to see, all the scientific literature and make it digestible for all of us. And we need more people like you in the world. And I could not agree more. But one question I had for you was, what video do you wish you could do over? So was there any project that you either failed at or that you have better tools to tackle now, or just something that you know have had a new idea on how to succeed better?
Yeah, I think if I were to do one over again, it might be the glass micro machining video. So for folks that haven't seen it, it's a video where I machined, in air quotes, glass slides using a laser. Essentially, it's a really neat technique that I forget the exact name, but essentially the wavelength of laser that I have doesn't touch glass, right? It just goes right through glass. You need something a lot longer, like a CO2 laser, to actually ablate the glass itself. But there's a trick you can do where if you put something underneath the glass that absorbs the laser frequency or wavelength, it will ablate and create kind of a pocket of plasma, which then melts the glass right at the surface. And so I did it with a copper sulfate solution underneath it and like filmed it and all that. But there's other ways you can do it using like graphite or even just metal underneath the glass surface. So I did that and it worked pretty well. I got cool etchings and you can very carefully drill through the glass if you do it just right. But that was right at kind of the beginning of the YouTube science section when I was just starting to get into the non-machining stuff. And I didn't have a lot of tools to analyze what I was doing. And so now if I were to do it again, I have a much better metrology set up, like different microscopes and stuff that we could really look at like what's going on. Is it melting the surface or is it just fracturing the surface? And just kind of the effects, how deep are these ablation craters? So I think it'd be cool to revisit that sometime, knowing what I do now and having more tools to get a better look at it.
Very cool. So you mentioned your laser. Let's get into what equipment you have. You know, you talked about your Avid and your OM, but you have a host of metrology stuff, a laser, all this. What goes into making your channel what it is?
Yeah, so probably the most prominent one is the laser, just because I've abused it for a lot of different projects. It's just an etching laser, basically. It's like the cheap blue box ones you get out of China that people use for etching serial logos or serial numbers or logos onto metal. And so mine's a 50-watt, 200 nanosecond laser. It's kind of its classification. So I picked it up. Nothing special. It's just you can find them anywhere on eBay or Amazon, and have used it for everything except what it's designed for, which is etching metal. So I've just used it for a lot of other projects. The wavelength is near infrared, and so it's just really convenient for a lot of different materials. A lot of stuff absorbs at that level, and they're pulsed lasers, so it has a high enough power that even if the material doesn't absorb it particularly well, it is enough because there's just a lot of power punched into it. So I've used that for a lot of projects, largely because it gets you, like, if you read papers and stuff, a lot of people have these really big fancy laser setups, and this laser gets you pretty close but at a fraction of the price. So it's opened up a lot of opportunities. From the metrology side, I don't know, I like microscopes too much, I think. So this is probably from my biology background. I used to work in a lab that did a lot of fluorescent microscopy, like fluorescent proteins inside of cells, and you take pictures of it and that would tell you stuff about your research. And so I've kind of carried that love of microscopes over to the material science world. So I've got a metallurgical microscope, like a one that designed to look at cross sections of metal and stuff. Regular, just upright microscope, a atomic force microscope, which is an interesting piece of technology, and a scanning electron microscope. And I think that's it. But yeah, I have a love affair with microscopes. It's part of like whenever I do projects, it feels like it's not a real video unless I can quantify it somehow. Like I really like to do a thing and then show why I know that thing worked. And you just need a lot of equipment to measure it. Otherwise, you're just kind of like making stuff up and putting it on the internet, which I guess is a valid strategy, but I don't like that for my channel. So
Yeah, I think that's one thing that is definitely special about your channel and that I really appreciate. Like I said, you know, quantifying all this stuff is not easy. And so a lot of people don't do it. And a lot of machining in general is just like, well, this has worked in the past and I've like experimented a little bit and it seems to work this way too. And so I'll keep doing this way. You know, it's a lot of guess and check, and even having like Justin the cogwheel on, he does design of experiments a lot, which is cool. Like that's at least a little bit more scientific and heading that way. So I think everyone appreciates that you can quantify a lot of that stuff.
yeah.
What kind of scanning electron microscope? Is it that tiny Chinese one? that I think like
No.
Strange Parts had?
Yeah, it's a similar idea. So it's considered like a desktop SEM as opposed to like the big floor standing ones that you'll see in a research lab. So mine is from Thermo Scientific. It's a Phenom XL for anyone that knows about SEMs. But yeah, it's about the size of like a suitcase and it sits on a desk. I got it because the specs are good enough for the stuff I need it for. It's not as good as a floor standing model. Like the big proper research ones are much larger and a better resolution and more stability to like noise and all that. But it didn't really matter for me. It has a big chamber and it cycles quickly, which is convenient because I can pop a sample in and out in like 2 minutes flat.
Oh wow.
So yeah, it's really convenient to just throw stuff in there. Actually, it's funny when I was talking to the thermo reps, he was talking about the people like who uses this because it doesn't get used a ton in research because it's not super high resolution. But he mentioned that like automakers use them a lot because you can have essentially inline inspection like of materials or coatings or whatever it is they need kind of along the manufacturing line, and it's easier and cheaper for them just to like throw samples in this essentially like shop floor SEM, check it real quick, and then get back to what they're doing. So it just kind of blew my mind when I heard that.
Yeah, I never would have thought that any of those automakers would have something like that. That's really cool.
Yeah,
Does
it's pretty
yours
wild.
do the X-ray analysis where you can tell like what kind of materials are in there?
Yeah, it's called EDS, or what is it, energy dispersive spectroscopy. And yeah, it essentially analyzes the energy of the X-rays that are being emitted when like an electron hits it, and it can use that to tell you in what proportion different elements exist. So you can get some really cool results. Like I was looking at some semiconductor chips, and you can see where there's obviously the silicon, but you can also see like titanium and tungsten and copper and all the different elements that are in a semiconductor, like a transistor. It's super useful. I think this is why they use them on the shop floors. You can check corrosions and coatings real easily that way. Like say you have a nickel electroplated surface and then there's a blob of something. It could just be like organic contaminant, but with EDS, you can see that, oh, there's a lot of iron oxide, for example, in that blob. And so like this is probably a pinhole that's then corroded and come through the coating. And so it takes it from a purely morphology based analysis where you're just looking at it visually to actually being able to see some like quantitative data about this is the stuff that's in this sample.
Yeah, that makes sense. That I had no idea that that was a capability of SEMs until I watched that Strange Parts video, and then I was like, "Oh, that's so cool!" Like that. That makes me want one just for that reason, you know.
Yeah,
Uh,
it's super cool.
well, that's great. And then, what makes you said you had a metallurgical microscope? What makes that different than a standard microscope? How is that tailored to looking across?
It's mostly just the it's a reflected light microscope rather than a transmission. So instead of shooting the light through the sample like you would with some kind of biology thing in a petri dish or on a slide, it's set up to bounce light off and get it back up so you can look at a opaque sample. Sometimes they're arranged differently where you set the sample down instead of up, and that's mostly just depends on kind of the configuration. I have a really cheap one though. Like nice ones have lots of fancy techniques like phase contrast or side angle illumination, different things to like illuminate grain structure and stuff better. Mine is just a cheapo from China, so it doesn't have any of that. But
Seems to work though.
yeah, it gets the job done.
So I had watched your low temperature sintering video too, which I thought was super interesting. Any thoughts on retrying that and try? Because I know you, I want to say that you said in the video that you didn't have the right type of oven for that, or something like that, or that you couldn't quite attempt it how you wanted to.
Yeah, I'm trying to remember the exact things I didn't have.
Because it
They
seemed
were,
like it almost worked. I was like so close. And
yeah, I still don't think it would work. I have some issues with the paper. I could probably talk a long time about how academia and papers don't reproduce nearly as often as they should. That is probably a rant for a different podcast. Yeah, if I think the biggest thing, my oven, so the furnace I used didn't have very precise digital control over temperature, which made it difficult to replicate how they ramped the temperature. So having a better controlled furnace would do that or would help. And then a few other miscellanea like mixing the ingredients up. I'm they didn't say, but I'm assuming they used like a ball mixer or something. It's you throw a bunch of balls in it and it spins it around at really high speed and knocks all the material together. It's like a tumbler on steroids, basically. And I didn't have that, which maybe would have impacted the results. I'm not sure. I don't. I just don't think that paper was a very good paper in retrospect. But that's science for
Yeah.
you.
Well, another question I had for you was what's something you'd like to do a video about, but it's too expensive or difficult to attempt?
Oh, well, there's some equipment that I would love to have, but is just way outside my budget for a fun YouTube channel. So the laser I have is considered a nanosecond laser. So the pulses are 200 nanoseconds, which is really fast, but in the scheme of things is like an eternity for materials. And
Right.
so if you look at like say you etch a piece of metal with this laser and then you go and look at it under the SEM, it's a really gnarly surface. There's these ablation craters and a lot of like recast material that is essentially molten metal that gets sprayed everywhere. And so it's just a pretty gross surface for what it is. But you can make faster lasers. So the next step up or down is a picosecond laser where the pulses are picosecond. And those are pretty cool, but they're relatively similar. And then you go one step further and you get to femtosecond lasers. So these are the laser pulse is confined to, say, 10 femtoseconds, which is, I don't know, it kind of breaks your brain to think about. It's like a trillionth of a second or something silly. And materials just react weirdly at this scale because it's a stupid amount of power in a really tiny amount of time. And it's fast enough that like most metals don't the material is ablated and ejected out of like the substance faster than the heat can diffuse into the neighboring region. And so what ends up happening is you don't get a heat affected zone. It just cleanly kind of like removes this material. So you get these super nice, well traced lines and metals. There's no heat affected zone. There's none of this like splattering of molten metal. And so that's really cool. And it also just does weird things in other materials because it's so fast. So for example, you can use a femtosecond on quartz and it shoots through the quartz because it's still transparent to the wavelength, but it like alters the chemical bonds just due to how much energy is going through the quartz at that location. And so you can do cool tricks like once it etches, well, once it alters the chemical bonds in this quartz, you can go back and etch it with a chemical solution. And those places that have been touched by the laser etch where all the rest of it doesn't. And so you can make these like 3D tunnels through a piece of solid quartz. It's
Oh,
just
that's
all kinds of
cool.
weird things. Yeah. So I would love to have a femtosecond laser because I feel like I could just abuse it all day long, but they're not particularly cheap.
What are they traditionally used for?
So they're probably most well known commercially for like eye surgery, actually. So I think
Oh,
it's
okay.
used in LASIK. It's like a green femtosecond that's used. And it's a similar idea. It's the heat energy is so fast and localized that it doesn't do a lot of damage to surrounding tissues. So you can do whatever it is LASIK does on your retina without like burning holes through your eye. They're pretty new ish. I don't know, 30, 40 years, which is moderately new. So they're not widely kind of used everywhere, but they're used a lot in medical micro machining. So a lot of like difficult alloys like nitinol, which would be difficult to machine other ways, is no problem for a femtosecond. And you get like a nice burr free surface for, I don't know, stents and stuff like that. And I think they're used in semiconductor fabrication as well for a similar idea. Like
Okay.
silicon is easily machined with it.
Very cool. Let's see. Another question about your videos. I'm sure you're tired of answering questions about those, but what's the most unexpected outcome of one of your experiments and videos?
Hmm. Well, I had a lot of papers that just didn't work, so those never turned into videos. I don't know if that's unexpected or not. I think the electroplating video was very surprising to me. Like I knew theoretically that it would work. For anyone that hasn't seen it, I 3D printed just tensile dog bone test samples, like you put on a tensile tester, just using SLA prints, if I remember correctly. And then I electroplated them in copper and nickel and just measured how much it would affect the tensile strength of these samples. And I was really shocked to see how big of a difference it made. If I remember correctly, the nickel plating almost doubled the tensile strength, which seemed crazy to me because it's only like a 2 micron thick plating. It was really thin, but even that was enough to just, I guess, spread out the stress distributions and really increase the strength. So that was very surprising, even though I knew it would make a difference. I didn't expect it to make that big of a difference.
That's really
Um,
cool. What about failures then? You said you had some that failed. Are there any that like you were sure was going to work? It was a slam dunk, and then it was just like nothing.
yeah. Oh, yeah. That's definitely happened a lot of times. And partially because papers present everything in such a cut and dry, like, this is how it works, and here's the results. And it's like you read it and you see the paper and you're like, yeah, I can do this. This is easy. And it never it never works out that way. The most recent one, it was also an electroplating paper where they made a super hydrophobic surface. So a surface that really doesn't like water,
Right.
essentially. And it was an electroplated surface, like a nickel electroplating bath, very standard electroplating, nothing fancy there. And then they included tungsten disulfide, like tungsten disulfide lubricant, the dry
Uh-huh.
lubricant. And they just included it, and you agitate the solution. And this is a technique kind of known as co-deposition, where the inert particle just gets incorporated into the electroplating as it happens, just kind of by accident. And you can do this with all kinds of stuff like aluminum oxide or diamond particles or Teflon or tungsten disulfide. And so they did it with the tungsten disulfide and made a super hydrophobic surface. And I saw this and like, this is perfect. I've got literally everything here. I have all their ingredients. They spell out everything about, the temperature and the current density, all the stuff. I did it. It didn't work. I tried it like 100 times. It just didn't work. I emailed the authors and never heard back. So I don't
Oh,
know. Like, there's probably one critical parameter that I'm getting wrong, and I just don't know what it is. Some secret sauce, but I have yet to figure that out. Actually, it's funny. I've got the video on my Twitter of dropping a drop of water onto it, and it spreads out immediately. It's like a super hydrophilic surface rather than hydrophobic. So I don't know.
the exact opposite of what you're hoping for.
Yeah, exactly.
Oh boy. So how long does a video usually take you? Like how much work did you put into that before you were like, well, that was a waste?
Yeah, it depends on what the video is. Some are kind of long burns where I poke at it repeatedly over the course of a month, but I'm not spending like full time on it. That one was probably 3 or 4 days of just electroplating experiments before I gave up. So, yeah, quite a few hours. I have like an array of 30 some samples that I tested, trying different configurations and tweaking stuff. So sometimes they can be a significant amount of time that just doesn't go anywhere. The worst ones, that one was at least like it just didn't work. And so like, okay, I could quit and move on. Sometimes they kind of work, and those are almost worse because you get lulled into this false sense of like, oh, I just need to spend a few more hours and I can get this fully working, and then it doesn't. The sintering silicon carbide was kind of one of those where I got just enough of it working that I'm like, okay, let's just keep crunching at this. And that was like weeks of effort before I finally just gave up and made a video about it.
Yeah, you could tell your frustration. Like you were very obvious, but like just listening to it, you're like, yeah, the paper wasn't great, and this is like, it's like, yeah, I'm sure that gets frustrating when you're like, it should work and it doesn't, you know.
Yeah, that's science for
Yeah.
you.
Well, I wanted to talk about your most recent video too, the JWST stuff, because it was really cool. Like I've seen those structures before in machine tools or Delta printers or whatever. So it was really interesting to see how they're using it in such a different way, and then that reversing mechanism, going from fine to coarse is such a genius idea. So how did you like?
Yeah.
What's your thought process, and how did you stumble across that? And then how do you plan a project like that?
Yeah, so that one I heard about it through a different podcast, the Orbital Mechanics. It's like a super nerd podcast for astronomy people, anything like space flight related they talk about. So they were talking about it and like just how cool the mechanism it was, and they were trying to describe it. And it's kind of hard to like visualize this through a podcast format because it's just a really complicated mechanism. So I think I was driving up to my shop or something while listening to the podcast, and when I got home, I pulled up the paper they referenced and started looking at it. And like, this looks not entirely impossible to like reverse engineer. The paper was kind of somewhere in between like a white paper and an actual academic paper. So it didn't spill all the details, but it laid out a lot of the important bits. So there was some important critical dimensions about, the size of different components, and the gear train was laid out pretty precisely. And it looked like the drawings in the paper were basically technical drawings that they'd slapped in there. So everything was kind of to scale. So I just decided one, it would make a good video just because it's a cool mechanism and JWST is like the thing right now. So from a YouTube perspective, it made sense. And it was also just a really cool mechanism. Like I just loved everything about it. So I threw it into Fusion, basically made two canvases 90 degrees apart because they gave a front view and a side view and then a few other kind of accessory views, and then just started CADing from there. So blocking out like the main mechanism and then using like a gear plugin to generate gears that were pretty close using their ratios, and then just kind of fiddle faddling around to get everything lined up. The biggest problem for me was that they used a lot of bespoke kind of custom stuff in the mechanism. So they had these really tiny little bearings that I assume, well, you could probably buy them somewhere, but they were very small and I didn't have any on hand. So I had to kind of enlarge certain part of the structures to use the tiny bearings that I did have on hand. And then like they had a custom made ball screw, which you just can't buy. So I used like an M8 regular screw. Yeah, I just kind of like futzed around until I got it into something that was working. And to be honest, I didn't fully understand the mechanism until I really got done CADing it up, because just parts of it didn't quite make sense to me until you could see a 3D model. I'm like, oh, okay, that's what this thing in the back is for, is it's, holding on to this part of the mechanism.
When you were describing it in the video in the beginning before you showed the thing, I was the same way. I was like I understand the words coming out of your mouth, but I don't understand how they link up. And then you showed the model. I was like, oh, sweet. Okay, this is cool. So for anybody listening who doesn't know what we're talking about, the JWST is the James Webb Space Telescope, and it has all of these mirrors that have, is it a hexapod? Or
Yep.
So the hexapod where there's what, 3 of those per mirror, and then there's a bunch of mirrors.
Let me see if I remember. So there's,
I guess hex would be 6, right?
There's one hexapod per mirror, and there are 3 sets of 2 actuators that make up the hexapod on the back of the mirror. And then there's a 7th that controls something else. And then that's per segment. And I don't know, there's like 30 segments or something.
Yeah. And they have this crazy fine to coarse mechanism that is just so cool. I've never seen anything like that, where you just keep rotating the motor and all of a sudden grabs the course and just starts, doing course adjustments. And the accuracy of this thing is just mind boggling. I mean, it was down into nanometers, right?
Yeah. It's kind of silly when you look at the specs. The course range was like 21 millimeters. So 2 centimeters is the total travel, which is enormous for something like this. And the fine step range was like, I don't know, 50 microns, something on that order. But the resolution, I believe, was 7.1 nanometers. So each step of the system took it 7 nanometers, which is just, it's wild.
It's insane. But it was really cool. I appreciate you printing that too. And like the fact that, anybody can go and experiment with that. Is that one that you would like to kind of do a full mirror segment of at some point?
Oh, I do. I'm trying to convince myself not to, because that would be a lot of work, but I do. Yeah, because the actuator is super cool, of like just how it works. And we need to make a slightly less janky version. So if anyone's watched the video, it works. It definitely demonstrates the principle, but it's like wobbly and kind of janky. So making a nicer one out of metal, for example, would be pretty cool. But it's only a portion of the really cool stuff. So the actuator, the part that moves, is connected to these like athermalization brackets. I think it just separates the heat of the system from the mirror. So it's connected to those brackets, and then those brackets are connected to 2 spherical flexures that allow the hexapod to move in all dimensions, essentially. And then all that assembly is on the back of this mirror segment, which has this cool like waffle iso grid on the back. And then there's a 7th actuator in the middle that controls the curvature of the mirror, which is super cool. And so, yeah, I would just love to have one of those built. It's tempting to do a to scale model, because the actuator that I made in the video is actually to scale. Like that's the size of the actuator, which
Oh,
is
no
kind of
way.
cool. Yeah,
Wow.
it's only like 150 millimeters tall, which is really cool. And so it's tempting to be like, all right, well, that's to scale. Let's make a mirror segment to scale. But that's a mirror segment's like a meter and a half, something like that. It's pretty big actually. So that would be a large undertaking.
That's crazy that they have that small of an actuator on such a large mirror segment.
Yeah, yeah, it's pretty wild. The stepper motor they used is actually smaller than the stepper motor that I used. So I used one of the cheap, oh, I don't remember what they're called, 28 BYJ something. I don't know. They're like $1.50, super common Arduino baby's first stepper motor. And the one they used is even smaller than that. And it's the amount of engineering that went into this is pretty remarkable.
That's crazy. Well, then, I mean, all of it was so cool, but the thing that blew my mind was that it was Ball Aerospace. I know somebody posted it
Yeah.
on the Discord, and I was like, wait, like the Mason jar company? And
Yeah.
apparently they have had a aerospace division forever. Like it's, one of the longest standing aerospace companies in the US. So that was such a mind blowing thing that like such a large, such a different branch of theirs is the only thing I knew about them. And then I was like, oh yeah, and also they make aerospace stuff like missile stuff and telescope and all kinds of stuff. So that was
Yeah,
really
yeah.
cool.
I had the same reaction because I had seen Ball Aerospace when I was looking at this paper, and I'm like, oh, okay, Ball Aerospace, whatever. Names are shared all the time by companies. And then I saw the logo. I'm like, well, that logo looks a lot like the canning jars on my table.
Yeah.
And sure enough, yeah, it's the same company. And they, when I started looking into it, they've done a bunch of stuff. Like they made the corrective optics for Hubble, like back in the 90s or whenever when Hubble needed to be fixed. They
Oh wow.
made the optics for it, and they've been involved in a bunch of satellites. And yeah, they're actually quite the company. I had no idea.
That's great. If you haven't seen it, speaking of the hexapod, there is a video. I think it was a Kuma that had a octahedral hexapod CNC
Oh,
back.
that's cool.
I want to say it was late 90s, maybe even early 90s. I think them, and then I think it was Ingersoll Rand while they were still building CNCs. They both had octahedral hexapod where the spindle is suspended from the hexapod. So through
Oh,
actuation, you can actually turn the spindle at different angles and drill and mill and all that stuff. And there's
that's
a
cool.
a few videos. I mean, they're terrible potato quality videos, but it's still really cool. I'll throw it in the show notes for anybody who wants to see it. But they're absolute bananas machines. One of my instructors in school used to work for Ingersoll and said that like they, because of the hexapod, the machine didn't even have to be level at all to cut a good surface
Hmm.
because the head could just account for it. Yeah, they're really cool. So I'll throw it in the show notes and I'll send you the link because it's just a weird. It looks like some kind of octopus machining
That's
with a
awesome.
head. Yeah.
I love it. Oh, honestly, that's as kind of a software guy, like whenever I see problems in machining and stuff, I'm like, this is a problem that's fixed in software. Like, why are we spending so much time and money making precision anything when you can just calibrate it?
Right.
And so like I see stuff, I'm like, oh yeah, it's just map it out and fix it in post.
Yeah. Well, I mean, it's starting to get that way with 3D printers and all that, being able to bed level and
Hmm.
a lot of that's so nice. What 3D printer do you have? Because that was all 3D printed for your JWST video.
That was printed on an Photon Mono X, I think, if that's the right name. Yeah, I've got an old Elegoo Mars, like the first version, and then a Mono X. And they're both SLA printers, and then some crappy FDM printers. I don't know, Ender 3 sort of thing.
Yeah, that's what I've got. I'm looking at it right now, and it's heavily modified to make it where I was happy with it.
Yeah,
I probably should have just bought a Prusa at this point.
I should have as well, because I don't I don't do 3D printing because I enjoy it as a hobby. Like some people really love it as a hobby, and that's great. I just want it to work and make me things. But I'm also cheap, and so I always buy the cheap one, and then ends up being a project to fix and make it work. I'm like, I should just buy a Prusa and just be done with it.
Yeah, yeah. At the beginning, I enjoyed the hobby aspect of it, but now I'm at the point where I'm like, can you just make me things? And like
Yeah.
I've gotten to the point where it's reliable. Like I remachined or I made an entire bed mount for mine so that it got rid
Mm.
of their crappy plate. I got like the direct drive, bed leveling, all that stuff. But yeah, at this point, it's like, man, I'm probably in it what I would have spent on just a Prusa, and that
Yeah.
thing would have printed dead nuts perfect every time. So
Yeah, and saved you a bunch of time on top of it.
yeah, exactly. Because now I'm at the point where I'm like, I just want you to print this collet tray so I can store my collets. Like, I don't
Right,
want to screw
yeah.
around with it. But
Yeah.
well, let's talk about your machines a little bit. I want to talk both about your OM and the issues you've had and what your plans
Mhm.
are for it, and then also your now baby Datron that you're trying to.
Yeah.
So, which one is? I guess you've been posting a lot about your Avid that you're
Yeah.
solidifying. So let's go into that.
Okay. Yeah, so I have this Avid CNC. It's, let's see it. For folks that aren't familiar, it's just a gantry style machine. It weighs maybe like 300 pounds, 400 pounds all up. So it's pretty chunky for a desktop machine, but it's still a desktop machine. And since I've been using it in metal with a high speed spindle, well, high-ish, 24,000, it needs to go fast to make any sort of progress. And being light enough, it kind of starts walking around the table when you do that. So anything over like 100 inches a minute, it starts kind of vibrating itself around, which I can't imagine is great for anything. So I recently moved shop, and it was partially disassembled from the move. And I just started looking, I'm like, oh, maybe we could beef this up before I get it reassembled. So I mounted it onto an old lathe base, which I'm sorry for anyone that likes old lathes. I've desecrated an old Logan for this project. And it's the lathe base is, it's old 80s style steel weldment. So it's pretty thick and heavy in of itself. And then I filled kind of the space in between the table. So if you take the table off on the Avid, there's four big aluminum extrusions that connect the two Y rails. And I filled all of that with essentially epoxy granite, less cosmetically and more just for like mass. I don't think it'll probably add a whole lot of stiffness just given where it is in the system. Like I don't think it's gonna contribute too much, but it did add about 300 pounds of extra mass to everything, and it kind of bolts it down to the table so it doesn't walk around as much without actually having to bolt it down.
Well,
So
I
that's,
imagine it ties those Y rails together at least more than just the ribs did.
yeah, I'm kind of hoping that's the case. I contemplated like trying to do something to quantify it and just decided I didn't care enough, and it was just kind of YOLO it and see what happens.
Well, I
Um,
imagine since you have that chatter video, you could pull video from there and do the exact same cut now and see if there's at least any difference. I mean, it's
yeah,
less quantifiable, but you'll at least be able to see if there's significantly different chatter.
yeah. Someone mentioned that in the Discord. I'm like, oh, that's a good idea. I should do that. And if I remember correctly, I did just easy straight cuts, so it would be real simple just to compare and see if I can grab the same microphone and stuff and do a straight comparison. But that was fun and a lot of work. People don't tell you online how much work it is to like hand mix and pour 300 pounds of sand and gravel. That sucked. It was like 4 days of not a whole lot of fun. And then now I'm kind of at a point I'm not sure what I want to do next. I was originally just going to do that to add mass and then put the table back on and reassemble everything. I am going to swap out the steppers for ClearPath servos.
Oh,
Um,
sweet.
yeah, I'm pretty excited for that. If there's one thing I regretted about the machine, it was the motor selection. So Avid can sell you either NEMA 23 or NEMA, what's the next one up? 34? The next size up, essentially. And I opted for the 23s, which in retrospect was a mistake because you can miss steps at times if you're moving too quickly and stuff like that. So I decided rather than fussing around with steppers, I'm just going to go straight to servos, and clear paths are easy. So that was kind of the right option. So that's kind of next on the to-do list. But now I'm looking at the X gantry and I'm like, well, maybe I should do something with that. And it's a terrible idea to at this point. But the way Avid's got it set up is the linear rails and the ball screw are attached to kind of like a mounting plate, and then that plate is attached to an aluminum extrusion. So you can demount all the fussy bits that need alignment and remount it onto something else. And so I could replace the whole X gantry with something stiffer if I wanted to, or more lightweight, or both, depending on how you do it, which is tempting because that's right, the biggest downside to these grouters is just the torsional stiffness of that X gantry just isn't very high. And so if you could replace it with something stiffer, that could be interesting. So I've been spending too much time in like generative design and fusion, letting it churn through fun shapes. I'm like, oh, maybe we could 3D print this and then do a carbon fiber layup of it. And it's all a terrible idea, but it could be fun.
Yeah, that sounds fun. I mean,
Yeah.
it can still be fun and be a terrible idea. I've
Yeah.
had plenty of those. So
It's like, it's funny because on one hand, I'm like, oh, this would make a great video. It'd be super interesting and I'd learn a bunch. And then on the other hand, I just want a router that does work. And it's very possible I could end up with a router that doesn't work as well as it did before because I'm a terrible engineer. And so trying to weigh the two pros and cons there.
yeah, definitely. Well, let's talk about your OM because you've had some trials and tribulations with it. What's going on there?
Well, that we can chalk up to naivety, I guess. I assumed I would get a used machine and it would work. I guess that was a big assumption. So yeah, I got this machine. It was a little while getting it set up. I had to do some electrical and stuff in my shop and got it running. I did my first test cuts and it went great. And I did my second test cuts and it made a really bad noise and stopped working. And as it turns out, I'd blown the spindle belt, which was exciting.
Oh boy.
I don't know if that was my fault or not. It might have been my fault. I accidentally plowed it into the workpiece a bit more aggressively than I'd intended. There was an offset error when I was like probing stuff. And so it took a chunkier cut than it was supposed to at first. And maybe that like stressed the belt and then it gave up the ghost. But I became acquainted with how to change the belt and how to pull the spindle apart, or part of the spindle anyway, which was exciting. And then the lubrication system to the spindle started throwing errors. And it turns out, so it's got like one of the, I don't know how to pronounce it, Bijor, the oilers that are used on all the Haas machines. It uses an air oil mix, and that was all clogged up with this really gunky old oil because it had been sitting around for Lord knows how long.
Yeah.
So I pulled that apart, cleaned it, got that working, and while the covers were off, I kind of noticed that the grease was not looking so hot to the grease lines to it. So this machine uses a external kind of like battery powered grease canister that I think it just shoots some grease every so often on a timer, but there's no sensors or anything as far as I can tell. It's totally external to the machine and it just looked not great. And so I started looking into it a little bit more and they're definitely clogged.
Oh,
So
no.
I've been currently pulling apart the grease lines, trying to get it unclogged. I grabbed like a manual grease gun. I was just trying to like add pressure to it, see if I could unclog it that way. And that did work for some of the lines.
That's
But
good.
now, yeah, it's kind of a good and a bad because now it's unclogged some of the lines, which means there's no longer pressure in the system. And so any more grease, yeah, you pump through it, it just shoots out of like the one carriage block that's unclogged.
Right. That makes sense.
So yeah, so I've got more of the covers off. I'm currently pulling apart. People in the Discord have been hearing me complain about this for a while now because I keep posting like, I don't know what to do now. The machine is so tiny, like everything is stacked on top of itself differently than a lot of other Haas machines apparently, and it's just very difficult to service. Like the manifolds you can't access without pulling parts of the table off, and
Oh
it's
no.
just, yeah. So I don't know. I'm debating. I'm at the point where I basically need to fully strip the X and Y axis or call Haas and have them do it for me. And I don't know which is the better at this point.
Right. Yeah, that's all of those systems are so tough to both service and, long term you're like, oh, this is going to be a pain point. Like I know on our Kitamura, I think it was maybe just for a day or two, we had an air oil spindle and I think one of the lines was starting to get clogged up and we just like there's a manual pump button on it. We just kept pumping and pumping and pumping and then it seemed like it finally got most of it out and we'd have any more issues, but that's a pretty common failure for those spindles is that the top one will get clogged. And then, like you said, once there's a path of least resistance, it just all goes down there. And so the top bearings don't get any oil. And then you're running at 15 grand and it just pops or something. So we got really lucky. Yeah. Well, that's unfortunate, but I'm looking forward to seeing what you do with it. Cause like I said, I mean, that's a perfect machine for what you're trying to do. So it'll be really cool to see what's going on.
Yeah, it'll be great if it starts working someday. I don't know, it's gonna be the death of me.
Well, let's go into shop news and new things. I don't know if you can share what your next video you're working on is, or what's new in your shop. What's going on there?
Yeah, so in shop news, well, I moved shops. That's probably the biggest news, which has been a huge hassle. So I used to just work out of my garage. At some point, it made sense to move into a proper shop and just made like insurance easier and getting out of the house and stuff like that. And not having to justify why I was putting another piece of large equipment in our garage, that sort of thing. So I've got a shop space I've been slowly moving into, but it's been a long process because there wasn't heat for a long time, and I'm up in the Northeast where it gets quite cold. So having heat in the winter is pretty important. But I'm basically kind of all my equipment's mostly moved in and setting everything up slash playing around with the OM2A and the Avid. I don't think there's any been new purchases for the shop itself. As far as projects, I've been working on, it was called photolithography, and I don't know how much the machining crowd would care about this, but it's basically like a really tiny printer is probably the easiest way to put it. Like you lay down photoresist, or if anyone's done PCB work before, it's very similar to that, like a photosensitive resin that you lay down on a material, and then you can trace patterns over it and then develop it, and it leaves holes in the photoresist, and then you can do stuff like etching or whatever. So I've been building a small photolithography machine to do more microfabrication sort of work.
Oh, cool.
And
I've
it's
seen kind of large scale stuff like that. I don't know if you follow King Tutley on Instagram. He's
I,
actually local to me, and he makes a lot of like reproduction nameplates for like old machinery or old cars or stuff like that. And it's, I think, probably a pretty similar process,
yeah,
just at a large scale.
yeah, it probably is. Yeah, it's interesting. So I think it's used a fair amount for like, well, obviously all the semiconductor stuff uses it, but as far as like metal work, I think it's used a lot for like creating masks or anything that like thin metal that you need very precise etchings through. You can lay down a photoresist and generate like these very tiny features through the metal. So that's something that I was going to look into, is using it for kind of microfabrication of, say, I don't know, like small gear parts or like watch hands, that sort of thing, you could do with an etching process pretty easily. I
That's really
also
cool.
saw a paper, which I'm tempted to try. So there's a process called electrochemical machining, ECM, and there's a way you can combine that with a photoresist. So you lay down the pattern in the photoresist, and then you apply your electrical potential, and it etches only in the parts that have been exposed through the photoresist. And then everything that is covered up by the photoresist doesn't etch. And so it's a way to get a similar idea, but with like an electrochemical approach.
Oh, very cool. That could be awesome. Well, great. That brings me to the last question I ask every guest, which is, what did you research this week? And it doesn't have to be machining related, doesn't have to be science related. It's just what's been popping up in your browser and that you've been kind of nerding out on.
Well, so I've been doing a lot of carbon fiber research for this. The other thing, so I kind of go through like phases, and I'm in a machining phase right now since I've been working on all these shop tools and stuff. And one thing that's always kind of bothered me as a software guy is that it doesn't seem like machine tools are like in the same century as the rest of everything. Like, this is admittedly a very biased view. I've mostly worked with hobby equipment or like equipment from 2000 whatever, but it seems like even high-end machinery is pretty dumb, right? You tell it to do a thing and it'll go plow through that workpiece whether it makes sense or not, or hit the table. And so I've always been interested in like sensor fusion with machine tools. So accelerometers on different axes, vibration measuring, kind of like active chatter control on the spindle or on the fixture. So I've been doing a bunch of research lately just to see like how hard it would be to make a smart fixture, for example. So there's some academic research looking at, say you've got like a vise or a fixture plate or something that has some way to move itself. So it's got piezoelectric actuators or electromagnetic actuators, and it can actually tell when it's chattering and resist the chatter by kind of exerting a force in a different direction. So it's like actively fighting the problems in your system. Yeah, it's a really neat idea, and it's still not like as integrated as I would like. Like, really, the machine controller should also know about this, and they should work together, and it should be kind of a unified system. But on the other hand, it would be something you could just drop on a table, be like, it'll make things better because it knows what it's doing, and it doesn't need to interface with your 2005, Fadal or something. So yeah, there's a lot of neat research there. Similar ideas with like spindles you can have active chatter control in the spindle itself. So if it notices the tool is deflecting, it can kind of add an extra force the other way, either in the spindle or like tell the servos to give it a bit more juice, or varying the RPM of the spindle to try to get you out of kind of the instability lobes of like the chatter region.
Yeah, I know Akuma has that as an option, I think, on all of their
Oh,
machines.
do
It's
they?
called like machining Navi or something. And I believe you give it a plus or minus on feed rate and spindle speed, and it'll adjust those parameters to try to get out of chatter.
That's cool. Yeah. I wish there was more of that, or maybe there is, and I just don't know about it. But it seems like that should be standard everywhere.
You would think so. Like you said, it's 2022, like that, and it's not. None of those are expensive sensors. It's expensive R&D, and then
Yeah,
it should be a relatively easy thing. But I don't know if you've seen the company Karen Engineering,
it sounds familiar.
but they do a lot of that stuff. Like they have a power sensor that they'll put on spindles, and like all of this metrology linked with machine tool stuff, and tool tracking and chatter tracking and all that. They are doing a lot of that work, and I'm surprised that somebody hasn't just licensed their technology at this point.
Yeah, that's cool. I mean, it feels like that should be everywhere because I understand why it's not. It's expensive, and if it behaves how you don't expect it to, you could get results that you don't want. And a guy that's just trying to get parts done doesn't want to be fussing around with why his quote unquote smart spindle is doing dumb things. So I get it, but yeah, it seems like there's a lot of opportunity there to make these machines a little more self-sufficient.
Yeah, definitely. I look forward to seeing if a video comes out of that or something. I would love to see a smart fixture video or something along those lines. Well, Zach, I really appreciate you taking the time to come on the podcast. It's been great to kind of get to talk to you. That's always been one way, me watching your videos. So it's very cool to get to talk to you and then learn more about what's going on. And I'll definitely link, your channel and all that. I encourage everyone listening to go and check out Breaking Taps. Bunch of cool stuff. Really like all the stuff that I love to nerd out about that is probably significantly over my head, but I at least, leave the video being like, oh, okay, I kind of understand this concept a little bit more.
Well, thanks for having me. This was a lot of fun. I didn't feel qualified talking about machining stuff when I first got on, but this was a good chat. And I don't worry, I have no idea what I'm talking about in most videos anyway. Just kind of glossing over the high level details and hoping the real experts don't show up in the comments.
Well, thank you so much. And Patreon thank yous real quick. Thanks to Stefan for joining, past guest and now Patreon member. And thanks everyone for listening. I'll be back next week.